simple model, although you have to dig a little bit into the details before you can call it simple. Ami talked about partial solvability, and I will have an example about that. Many people talked about symplectic or SU11. You know, SU11 is isomorphical to SU2, so it is more or less the same thing. I was happy to hear that Jerry Dreyer mentioned both Rowe and Barry. These two people made a paper which I consider the best paper I have read together with Franco E5, the most inspirational paper I have read together with Franco's E5 paper. And so on and so forth. And then, as a quotation, Lincoln's book, it has a chapter that is called Phases, a perennial headache. And I tell you it's true. I had my real problem with phases. When your algebra is rank 2 or rank 3 and so on, is a pain in the neck. Okay, so a personal history of this work. I have read this very inspirational paper back in 2002, and a year later, or the same year, used it to solve the Bohr-Hamiltonian just after Franco Iacchello solved the E5 and X5 problem, and I had many, let's call them success or published paper with this algebraic technique. It was very, very useful. I don't have time to discuss all that. And then I got the idea to extend to 2 coordinates while I was in Belgium in 2004. Then I was trying to calculate matrix element and I failed repeatedly. In 2007 I met Rowe in Seattle and he said, could you, after a quarter of an hour I was talking of algebras and so on, he said, could you formulate your idea in mathematical terms? Well, that's what I'm trying to do. And then I have met a mathematician with whom I have learned, from whom I have learned a lot of things. And then finally, this year I understood that I should eliminate the finite dimensional representation from my mind and go to infinite dimensional representation. And then I found an easy way to calculate matrix element. That is what I'm talking about today. So let's go back to the paper of Rowe. So in the paper of Rowe, he introduces the algebra, he calls it SP1. Okay? Other people like me call it SP2, but it's the same thing. N equal 1 is the rank of the algebra. So if you have a problem in which you have a coordinate R, and in which you have the associated momentum P, then with R squared and P squared and another third operator which is not very important here, you can close you see that this commute closing, the commutation relation close into the structure constant of the SP2 algebra. And this is very general because you can take your R vector to be n-dimensional. So you can use it in 3 dimensions for molecule, in 5 dimensions for the Bohr-Hamiltonian, and so on and so forth. If you operate a suitable linear transformation, then you see that your SP2 commutation relation are nothing but SU11, there's a minus here, commutation relation. So they are isomorphic. Of course, when you have defined x1, x2, x3, you can go to weight and step operator, x0, x plus, s minus. Okay? This is a very important first step because you pass from physics, these are physical operators, to algebraic operator which are a reminder of the root structure of SP2. So this x plus, x minus, x0, and you must know the action on the basis states. And this is well known. It amounts to this matrix element, and this x0 is a weight operator. Just count how many n you have. While x plus, x minus, they have the effect of increasing n or decreasing n by 1, while maintaining the same lambda. Lambda is a Casimir operator, is the eigenvalue connected with the Casimir operator of SP2 representation. So once you know this, you can calculate matrix element. If you have a matrix element, then the thing goes like this. You have an Hamiltonian. You map your Hamiltonian to algebraic elements. If you have the algebraic element, you know the action of the element on the basis, and you can calculate matrix element like this. Okay? So you can calculate matrix element of your physical operator, and then you can construct your Hamiltonian as a matrix just by summing up matrices or multiplying matrices or the system. So for example, this algebra allows you to have an exact solution of this. When I say exact, I mean you have analytic things for the entries of your matrix, but of course you have to truncate your basis, because I forgot to say that this basis n lambda is fixed by the representation, but n goes from 0 to infinity. It was given in this plot, I should have said. And you can use this to solve several interesting problems in dimension, in 5 dimension. In fact, I will use that several times. So you construct your Hamiltonian matrices, depending on how this is done. And this is very general. You can take any polynomial in the element of your algebra, and then you just diagonalize the matrix and then expect. So I skip this. This was already also inspired to Franco work and to his student, but I don't have time to discuss it. So my idea, we come to the idea, was to enlarge or generalize this algebra to 2 coordinates. So in row algebra, row bar, you use only R and B. I had the idea, which is trivial at this stage, I would say, to use R1 and B1 and just redouble to some R2 and B2. This would be nothing but the direct sum of 2 sp2 algebra. And there is nothing very peculiar here. What is nice, I mean, the thing that put me on Haller back in 2004 was that if you take this 4 element and add other 4 elements, okay, you can close the Lie algebra SP4. Now these 4 elements look a bit nasty. They are a scalar product of this vector. But there is one very nice element, which is that it is R1 scalar R2. So this is an element that enters into the expression of the distance between the 2 particles. So you have one element for the coordinate of particle 1, one element for the coordinate of particle 2, and you also have an element, ZA, that allows you to express the interparticle distance. So think to the possibility. You can make polynomials of this distance. You can make function of this distance and diagonalize very complex 3-body problems in which you also have mutual interaction. These are the commutation relations. I swear that they close into the SP4 SO5 algebra. And you can also check that, apart doing that by hand, you can check the computer. So then you have to operate the first method. As Rho did, I also have to look at the root structure. So if you pass from your Z operator to the X operator, this is analogous to Rho. This is a redoubling, you call it Y, because you can write the root structure as X operator, Y operator, and then you have the 4 genuine SP4 operator that are translated or transformed into T operator. These are pseudo-tensor, pseudo-B tensor, B-spine, okay, B-spine. These are in correspondence with these 4 extra roots, which you can see in the root diagram of SP2, which is nothing but C2 in Cartan Weber. Then you need the second method. Once you know the root structure, and this was, whoa, very heavy to do, I had to go to the Weinberg's book. In Weinberg's book, a very nice method is given to do that for SP2. I had to generalize it for SP4, and that was a lot of work. So in this case, you have to introduce 4 bosonic modes in such a way that each operator conserves the number of bosons. If you do that, then you can map your X, Y, and T operator to bosonic operator. The action of this bosonic operator on monomials suitably defined is known, it's easy. You can use the Banizak-Chen trick to calculate matrix elements, and that is fine. The only thing you need to work out, and this was the real problem, is to connect your 4 quantum numbers with the n quantum number, which is the number of volume for particle 1, the Casimir operator that is connected to the angular momentum for particle 1, and the same for particle 2. If you do that, together with the trivial matrix element, which are just a redoubling of rows matrix element, you also can calculate, and this is what I have done, the matrix element of these 4 extra operators. It's not a difficult calculation, but it's tedious. And this is totally new to my knowledge. Well, let's look at the action of this operator. These are operators which do not, which couple different representation of the subgroup of the subalgebra sp2 plus sp2, but still within a single representation of sp4. So to understand what is their action, so what are they doing to the n, lambda, n, and mu, you have to look at the following diagram. So you can see n here, m here, and lambda mu here for these points, here for these points, and here for these points. So the action of t++ in this case couples this point in the representation to this and that. It took me 10 years to understand that. You might wonder, maybe you are not so smart, other people take a week to understand it. But I think that this was the real solution of the problem, which allowed me to do some diagonalization, which is what I showed you now. So to summarize so far, we have physics, we have coordinate and momentum. We map physics to some operators which I call Z. You recognize they form an algebra. You can make linear transformation of your algebra, and you know and you understand something about the root diagram this way. But then you are not happy with that. You go to supersonic operator because they allow you to calculate matrix elements. These are 2 matrices which I cut. So Z1, let me remind you, is P squared, while Z2 is R squared. So P squared, R squared doesn't resound with the harmonic oscillator. So if you do Z1 over 2 plus Z2 over 2, this is the harmonic oscillator of Hamiltonian. In fact, if I sum these 2 matrices, I get something diagonal. This is nothing but the sum for coordinate 1 and for coordinate 2, and you get immediately the diagonal spectrum. Then you can play the game and go to more complicated Hamiltonian, where Hamiltonian which are not linear in your matrix element. Then in this case you will have extra, you will have non-zero matrix element out of the diagonal. In this case you have to diagonalize a matrix, the entry of which are analytic, rational or irrational. And that is a very easy thing to do with a computer. So you can solve very complicated problems like R to the 4, R to the 6, and so on, or more complicated functions. So the trivial application is 2 independent harmonic oscillators. So I have worked out this in detail. If you take 2 independent harmonic oscillators, then they immediately map to your algebra, and this is the spectrum of a single harmonic oscillator. The spectrum of the 2 independent harmonic oscillator, of course, amounts to put 2 particles here. If you put 2 particles here, you have this entry. If you put 1 particle here and 1 there, you have this entry or the other particle. And they are, all these states are analytic, and they are labeled by the quantum number n, lambda, and mu, where lambda and mu are connected, as you can see here, to the angular momentum. So lambda equal 3/2 essentially means an S state, and so on and so forth. Then you can go to more complicated Hamiltonian, because, let me go back, this is not very challenging, because in the end I'm just probing the elements of the row algebra and its redoubling. So I'm not probing the new thing I have added. So I need a more challenging test. The more challenging test is provided by this Hamiltonian, in which I also put twice the Z7 operator and twice the Z8 operator. So if you play a little bit with this is nothing but an harmonic oscillator Hamiltonian for the interparticle distance, okay? So that was a good check. I take these matrices, I take big 50 by 50 matrices, they are filled with numbers, and if you diagonalize them, you get integers. So this means that the various t++, t minus minus, and so on operator cook up in such a perfect way to give you the exact solution. If you do that, then you are confident that your t operator are fine, that the calculation of the matrix element was fine. This was just checked. And also, of course, the right number of degeneration, the right degeneration packets, that is very important. Okay, I don't discuss this because I think I don't have time. Let me go on to a new analytic solution. Actually, this is not a very difficult problem, but it was another test case I tried to do. The solution to this problem